people. All right, let's see. Let's go up to the board first. We kind of have our drug diagram here with a lot of different drugs, and I think we went through this a time or so ago, and we talked about stereocenters, and some of these are not chiral. There are no stereocenters like sulfa drugs, aspirin, sildenafil, Xandy, no stereocenters. But even some of the simpler drugs like methamphetamine, Prozac, cocaine, certainly there's 2 stereocenters. Somebody did ask about nitrogen, the lone pair on a nitrogen amine, and it is sp3 hybridized. Is that a stereocenter? Well, it turns out that you can invert that. The lone pair can tunnel through the atom and invert that. Technically, it is a stereocenter. The lone pair would be the lowest priority group. But that barrier to inverting that stereocenter is so low, we don't talk about amines as being chiral that way. So no stereocenter on the amine. So I'd just say 2 there where the esters are. Penicillin, how many stereocenters? 1, 2, 3 right there. AZT, 1, 2, 3. You can kind of just count them up a ton in FK506. I'm not going to count all those up. That's kind of like cholesterol, right? We said there were 8 stereocenters in cholesterol. Same with Taxol. Oh, a lot there. Prozac, just the 1. Is that stereocenter in Prozac R or S? Have you practiced that enough to see what the stereocenter is there in a simple drug? So there is the stereocenter. That's what we'd circle, right? And then how do we determine R and S? We need to assign priority to the 4 different groups on there. So there is a hydrogen on there, right? That's the lowest priority. And then what comes next? Oxygen or the 2 carbons? Oxygen, right? So that's the top priority. And then this carbon over here and then that carbon there. Now we're rotating what? Counterclockwise, looking at the front here. But we got to put that hydrogen in the back and rotate in the back, right? Looking at the back of that carbon. So that would indeed be what? The R enantiomer of Prozac, okay? The S enantiomer is known. It's not a potent drug. The R one here is. Anyway, okay, here's another useful thing I think to practice from or to keep these definitions straight. So isomeric relationships, I made this a while ago with a ton of examples here. So it's kind of a decision chart, a flow chart here. Identical structures, yeah, all connected the same stereochemistry. These are all identical. And then different connectivity, yeah, constitutional isomers. Anything beyond this is stereoisomers in 3D space. Conformational, if they're related just by rotating around a sigma bond. Can practice some of those. Some of them are different views. You have to tumble them in space and look at them carefully. The other one, enantiomers related as non-superimposable mirror images. That's a question you ask to determine whether something's enantiomeric, right? It lacks an internal mirror plane, so when you reflect it through an external mirror, you see all the stereochemistry is inverted, right? That's what a mirror does for you. And if they're related, it's non-superimposable mirror images. Yeah, they are enantiomers. You look for RNS, and that's an easier thing, I think. Multiple stereocenters in just 1 or more, but not all, are inverted. Those are diastereomeric. And then we have cis-trans isomers. Technically, these are diastereomers, okay? But it's rotation around a carbon-carbon double bond, okay? Cis-trans. And we'll get into alkenes later, unfortunately. We haven't had a chapter on alkenes yet, but we will talk about that. We've talked about, cyclic structures with 2 or more groups, across or together on the same side of the plane. So like this one here is the cis form, this is the trans form. But you can also assign R and S to each one of these stereocenters. This molecule is chiral, okay? So you'd see that one is the same, and that's the methyl stereocenter is the same. And then the hydroxyl stereocenter is different. So those are diastereomers. But they're arrayed cis and trans on the cyclobutane there. Anyway, so that's a good thing. We'll get into plane polarized light and talk about optical activity today. This is the plus minus, so the DL relationship. This is the physical property of these molecules. Let's start by reviewing one we looked at last time, this dibromo butane. And the issue there is, assigning stereochemistry chemistry, R or S here. What's this one here? That's indeed S. And what's this one here? That's indeed R. Okay. And notice we've got symmetry. The ends are the same. The groups are the same. So we have the possibility of what? Meso compound. Okay. And this is indeed achiral. It's a meso compound. There's a center of symmetry right here. All those atoms are reflections through that center point. And also, if we rotate around this bond, we can then see what? A mirror plane relationship here. Okay. This is still the SR. I didn't change anything or break any bonds. I just rotated around that sigma bond here, right? So these are the same molecule, but you can see now this mirror plane right here, right? So this S stereocenter is a reflection of the R here. So it is achiral, okay? If we do the optical rotation, it will indeed be 0. It will be optically inactive. Achiral molecules are optically inactive. They don't rotate plane polarized light. We're going to build a polarimeter right there on the overhead projector here in a second. But what do we call this? It has stereocenters, so we call it meso. Mesomeric, okay? It is symmetric. It has a mirror plane symmetry or center of symmetry. It makes it achiral. Will not reflect or rotate plane polarized light at all. Okay, let's go to the tartaric acids here. These are known compounds. They're added to candy and other food materials. They're all sorts. They're available in all sorts of fruits and vegetables. It's the tart flavoring. Okay, if you had the super sour candies, makes your mouth pucker a lot. Yeah, it's this guy. Okay, and you see 2 carboxylic acids, and then the 2 stereocenters. Let's assign R and S here. Let's see which one's which. Here's our stereocenter. Do them one at a time, right? So top priority group's oxygen, then the 2 carbons, hydrogen in the back. So hydrogen in the back, good. So when we rotate here, the next higher priority group is what? This carbon, because it has 3 oxygens on it, right? So everybody okay with that? 2, 3. So how are we rotating here? From the top priority to the second to the third, and that's what? Counterclockwise or clockwise? That's counterclockwise. So what's the stereocenter? S, very good. And this one's also S. You can see that right in the front there. So can we draw RR here? And you're told to create a molecule that has an enantiomeric relationship. And to do that, we have to invert all the stereocenters, right? So we can easily do that. That's the nice thing about the dash and the wedge. Once you're sure that that's in stereocenter, if you exchange the hydrogen and whatever other atoms are in that functional group, you invert that. So you can do your test there. That will indeed be R. And then, yep, RR. Okay, here. Okay, RR. Those are enantiomers of each other. Let me give you a little information here. 171 degrees C for the melting point. These are solid materials. This one also has a 171 degree melting point. And that's the thing about enantiomers, all the same physical properties. Okay, there's only 2 that are different. Optical rotation, direction, and what? Interaction with other chiral molecules, or their biological activity with chiral receptors, proteins, right? So 171 exactly. Okay, let's make a diastereomer of this. So let's invert that one to the R, and then keep the S here. Okay, indeed, those are diastereomers, the RS one now. Okay, and let's check the physical property. What's its melting point here? Oh, it's 146. Okay, you see that's very different, right? It melts at a lower temperature, has different properties in the crystal state. So it actually has all its properties different. Even though it's just a stereoisomeric relationship, but it's diastereomeric, okay? These are diastereomers, not full enantiomers, okay? And let's draw the mirror image of this and question mark. Is this the enantiomer, right? So if we take this compound and invert both of those stereocenters, what do we get now? We get the SR. But is there something fishy about this structure here on the bottom? Are these really 2 different stereoisomeric compounds? Or are they the same thing? In fact, you can take this structure, just rotate it 180 degrees, and look, it lays right on top of this one. It would be superimposable on its mirror image. So therefore, we conclude what? If it is superimposable on its mirror, these aren't enantiomers. This is an achiral molecule. This is the same thing, right? And why can we say that? Well, we notice a center of symmetry here. R and S reflection stereocenters. All the atoms reflect right through that center right there. So this is indeed what? A meso compound. Okay? Different compound. So remember the 2 to the n expression to keep track of all the possible stereoisomers. That's the maximum possible. If you have meso compounds, if you have symmetry on the 2 ends, you might have a lot of combinations that are just the same. Okay? Kind of have to analyze that, but everybody okay? So we actually just have 3 compounds here. These are tartaric acids right here. This is called Resinous Acid. And we'll see its optical rotation is actually 0. Pasteur was the first one to recognize this compound. And he took the optical rotation, found out it was 0. And that's where the term racemic comes from. It's an old term from wine production, racemous acid. And that's what this is here. But it's really not racemic, okay? When we say racemic, we're talking about a 50-50 mixture of 2 enantiomers. So if we had an equal amount of the SS and the RR enantiomers in solution and did the optical rotation, it would be 0. And we call that mixture racemic, okay? So don't let me, using this term racemous acid here, throw you off, okay? This is an achiral stereoisomer of the tartaric. So yeah, it gets kind of complicated, but go back to assigning R and S, okay? And think about the symmetry, and then you should be okay here. Done a lot of relationships here talking about this. Here's a very important molecule, glucose. A lot of stereocenters, 1, 2, 3, 4, 5. Let's draw the enantiomer of D-glucose. We call it D-glucose or dextrose sometimes because it is dextrorotatory. It does have a positive optical rotation sign of plus 52 degrees. And that's the magnitude of rotating plane polarized light. We'll get to that. That's why it's called dextrose. Okay, if you look at the Ringer's solution, intravenous solution for people who are dehydrated in the clinic, whatever, it's 5% sodium chloride and glucose or dextrose. Let's draw the enantiomer of this. So how would we draw the enantiomer? What do we have to do here? We have to redraw all the functionality, but what do we do to the stereocenters to get the enantiomeric form? What do we have to do? Can someone help me out here? Yeah. Flip all of them. Yeah. So flip them, meaning all of them. So that one would have to be down because it's up in the original thing. This one right here would have to be up. This one would have to be down. This would have to be up. And this one would have to be up. And that would indeed be the enantiomeric form of glucose. If we took the optical rotation of enantiomeric glucose here, it would be minus 52 degrees. Okay. If we had a 50-50 mixture of these two, the optical rotation would be 0. It would be racemic, that solution. Okay. How about a diastereomer of natural glucose here? We just have to invert 1. Okay. So let's invert. Maybe, let's see, this one right here at the 2 position. I'm going to invert that one. I'll tell you why in a second. Just look at the relationship right now. Oh, that one still has to be, see, that one, well, I need to keep all the others the same. Okay, down there and also up here. Okay. So all of these are the same relative to glucose. This one in the back's still up. This one's down still. This one's up. This one's the different one. Down here, up here. This is actually mannose. Okay. Maybe you've heard of mannose. It's a diastereomer of glucose. Stereoisomeric relationship. It's metabolized differently than glucose and incorporated into different molecules in living cells. So there's all sorts of isomeric forms of glucose. You'll learn about others later on in 352 and in biochemistry. Okay, what else is there? Galactose, mannose, a few others, xylose. The most common one by far is glucose, though. Okay. But there we just do a simple analysis of what? If these are enantiomers, all of them have to be different. Diastereomers, one or more, but not all of them changed. Okay, does that make sense? All right, let's look at another example here real quick, involving alkenes. Okay, how about this molecule? Let's draw an enantiomer and a diastereomer of this. So let's see, what would its mirror image look like? Well, the mirror would still show a trans alkene here. Now, we haven't done alkenes yet. There is a homework problem where it talks about a molecule of alkenes in it. I think it's discodermalide, a drug with a lot of stereocenters we've talked about. But an alkene can also be a stereogenic group, being either cis or trans. Now, it doesn't have optical activity, okay? Because if we look at the mirror of this, this will still have this trans, but what? The stereocenter will be inverted, okay? So indeed, those are enantiomers of each other, non-superimposable. We can assign R and S here. Let's do this. What? We've got 1, 2, 3. So this is S, and this is R, okay? How about the diastereomer of this? What would we do? Well, let's invert the alkene. Okay. Now, remind yourself of what the term diastereomer means. It means isomers that are what? Not mirror images of each other. So certainly, this is now the cis alkene, okay? And the mirror of this would reflect it as still trans. So this is still an isomer that's not what? Not a mirror image, okay? It's a different type of isomer. And indeed, that is a diastereomer of that, we'd say, okay? It's actually a cis-trans alkene stereoisomer of it, but diastereomer is actually a broader term. Can we do the enantiomer of this cis-alkene alcohol? Yeah, the mirror would still have the cis, but the stereocenter would be inverted. Okay, this is still S, but it's S with the cis. Okay, and this is R with the cis here. And indeed, these are diastereomer. And these cross relationships here, what would you say there? Those, are also diastereomeric in their relationship. Okay, I think that helps you with that one homework problem. Keep track of that. All right, let's look at the physical properties here, the optical rotation thing. Let's go back up here, and this is kind of a strange thing. It impacts physics, chiroptical photo properties of different materials, and a physicist would be more interested in these materials here, this quartz material, and the interaction of photons, light with this. So here's a light source. You can get photons to come out of an incandescent bulb, whatever. And when they come out of a source, they're randomly oriented. Now, photons are just like electrons. They're small, weird particles that travel as waves, right? And that wave undulation between a peak and a trough has directionality to it. It actually creates two fields, a magnetic field and an electric field that are mutually perpendicular to each other. So we're just looking at one field here. Let's call it the electrical field. Okay, they're oriented randomly. So these arrows here are what? Vector magnitudes of, say, the electrical fields. Okay? So they're random when they're coming out of a light source. And actually, that's all wavelengths of visible light. So we could talk about what wavelength we're talking about here. But as it goes through this quartz filter, and these were noticed early on, quartz is a mineral material. It can be mined. It's made up of silicon and oxygen. But how those atoms line up in the solid state, they actually create these slits, you could say, that allow plane polarized light just of one orientation to come through. So we filter out all of the other incoherent light that's of the opposite orientation of the slits coming through the quartz. And we only see now the plane polarized light coming out of one orientation. And maybe you've played around with sunglasses. There's a lot of modern materials where we talk about this. So the Polaroid company can make them not with quartz, but with these plastic materials. And there's your sunglasses. Those are kind of fashionable, right? I kind of look like Elton John, maybe. I don't know. No, probably not. Okay. But they have directionality, so light can either come through or it can be filtered out. And you'll see that better when I go to the overhead projector. But this is with two quart filters here. Now, when we have the light going through a filter and then going through a achiral material, the orientation of the light does not change. Okay, so if it's an achiral material, a racemic material, or a meso compound, it will come through and you'll still see the light on this side with the same orientation. Well, you need to look at something with another filter here. So that's why I've got the two filters here. The direction, they've got tape up here to show you where the slits start. And then when you rotate it 90 degrees, they cancel out the light. And that's kind of a neat thing. So, okay, so here it is coming through. It's plain polarized light. And then the sample tube has the chiral material. And then it can either rotate to the left or to the right. As you look down it from this side, there's your eyeball. You have to change the observation filter to be able to see the light coming through. If it's rotated enough, you won't see any light at all until you reorient the observation filter over here. And it's that rotation here. Alpha, sorry, we use alpha as a designation for this specific rotation X. If it's rotating to the right, we call it dextrorotatory. If it's rotating to the left or minus that degree, we call it levorotatory, DL. And if it's a 50-50 mixture of the D and the L enantiomer, it's racemic, okay? I'll write a bunch of these values on the board here in a second. Let me write a few of them on the board and talk about it, and then we'll build the polarimeter. How's that? So we'll do that. We could go back to this one here. I've got some of the numbers for tartaric acid. Let's look at that one. So the SS one, we've got here, SS, yep. If you take the optical rotation here, it's equal to minus 12.4, okay? And that's in pure form. When you measure the rotation there, it has a levorotatory rotation, minus 12.4. If you know one enantiomer and you know its optical rotation, guess what? You already know the rotation for the RR enantiomer because they're equal magnitude but opposite direction. Okay, so what would the RR be? If the SS is minus 12.4, this rotation here for RR, yep, is plus 12.4. Okay, it's the dextrorotatory. Now be careful here. R stereocenter does not mean it's always plus. S does not mean it's always minus. In fact, there's no known physical connection between the observed optical rotation and the inherent structure of a chiral molecule. It's still somewhat of a mystery how plane polarized light, when it diffracts through a chiral material or a chiral medium, how it diffracts that light and changes its orientation just a little bit, okay? So a lot of physicists and physical chemists who work on that kind of thing. Chiroptical properties still kind of a mystery. In fact, if you want to win a Nobel Prize, figure out the physical connection between the magnitude and the direction of the rotation and the actual structure. It's not known yet, but we do know this. And what's actually weirder is this rotation is the same whether it's in solution or in the solid state. In fact, Louis Pasteur, the famous French bacteriologist, the guy pasteurization and the rabies vaccine, he would have won 2 or 3 Nobel Prizes if they had them back then in the late 1800s. They didn't, right? Nobel Prizes started after poor Louis. But he made this connection as a graduate student working with Bivot, who was an expert on these quartz filters. And he said, well, some materials, these stuff he got out of wine, these tartaric acids and resinous acid here, and he was studying them in the solid state and in solution, and he'd get these same rotations. And he said, well, there must be something inherently asymmetric about the structure. In fact, this was before organic structure was really determined, the tetrahedral nature of carbon. And now we can match it up and say, oh yeah, this is RR and that's SS, opposite rotation. But Louis made the deduction that there has to be something inherently unsymmetric about that. And then Resinous acid here, if you take the optical rotation of this guy, it's 0. It's achiral. Okay? It's the same. That kind of shows some relationships there. Let me give you a couple more here. Optic rotations. Let's see, I don't have those. Got some other ones we need to talk about. Oh, here we go. Been talking about these two. Need to get the optical rotations on here. Oh, and we need to get the names on there too. This is 2-butanol, right? Even though you don't need to know how to name alcohols yet, but the two positions where we have the alcohol on butane. Which one's the R, which one's the S? Because the S and the R go in the front of the name now, okay? So let's see, is this R or S? Are you getting better at that? 1, 2, 3 party, and that's rotating into the front. It looks like it's counterclockwise, but if you put it in the back, what is it? That's R, okay? Yeah, and this one's S. So in the front of the name would be S2-butanol for that one, R2-butanol for this one. I've got the rotations here. Oh, R is actually minus 13 degrees for its optical rotation. The S, and you know the S already, because you know the R in pure form minus 13. The S is plus 13. And notice the S one is dextrorotatory. And that's what the little d means sometimes, okay? Sometimes they'll say D there, or sometimes they'll just say the plus form, okay? And sometimes that's part of the name. It'll be DS2-butanol or plus S2-butanol, just to give you a sense of the rotation there. If you had a 50-50 mixture here, what would it be? It'd be racemic. And if you took the optical rotation, if it was 50-50, would it be 13, minus 13? No. One would rotate equally to the left, one would equally to the right, and you get a 0 rotation there. It'd be racemic. Okay? Everybody see that? Okay. All right, speaking of optical rotations, let's do a little bit on some calculations here. And yeah, there is a little bit of numerical analysis. I'll never put a problem on a quiz or a test that requires the use of a calculator or anything beyond just the fundamental equation. So optical rotation in brackets is called the specific rotation. Okay, and that's a physical property of a chiral, pure, and antimeeric material. There's a subscript D, which stands for the sodium D line, which is usually a uniform light source in a standard polarimeter machine. We'll use white light here on the overhead projector, so it'll be all wavelengths of light. Usually if you report the specific rotation for a chiral molecule, you'll have the sodium D line, which is 589 nanometers. Don't worry about that. And then the temperature is often specified in a superscript. Not always, though. The literature is kind of all over the place. You have to compare it to a known compound to make sure, whatever. But this specific rotation is equal to the observed rotation. And that's what you actually get out of an instrument when you do the calculation. And that's dependent on a couple other things here. The length of the tube, L, which is almost always in decimeters, which is a weird unit. None of these are SI units, by the way. 1 decimeter length, that's a standard length for a polarimeter to do the calculation. If it's a longer tube, you have more chiral material. Your observed rotation actually be longer. So this is why it's in the denominator, right? So if it's a longer tube, that detracts from that. Times concentration, and this is even weirder units, I think. The concentration is in grams per milliliter. It's not molarity, which is what, moles per liter. That's the standard unit for concentration. Sometimes I've switched it over to that, but these are kind of archaic terms. It's an archaic function there, but grams per milliliter. So yeah, if you have more material here, your observed rotation will be higher. So dividing by concentration gives you the specific rotation. All right, the calculations will be simple here. let's say if we have an observed rotation of plus 10, okay, it's a 1 decimeter tube, and there's 1 gram in 10 mils. What is the specific rotation? So I think you could set up the equation and do it simply without dealing with a calculator. And this is typical of ones I could ask on a test or a quiz, right? So the optic rotation is plus 10 divided by 1 decimeter. Good. You don't need to worry about that. And then grams per milliliter here. Well, this would be 1 gram per 10 milliliters. That'd be in the denominator of the denominator. So you'd switch that up to the numerator, right? And so what's the observed or the specific rotation in this case? It'd be 100. Okay. Yeah, we could have said 0.1 here, 0.1 grams per 100 mils, and that's what the thing is here, grams per milliliter. Yeah. So yeah, that would have been 0.1 in a milliliter, 1 gram in 10 milliliters. Yeah, so 10 times 10, yeah, 100 there for that one. So yeah, you see it's a little less concentrated, which means what? It's a higher rotation. Okay, another thing about optical rotation is the percent enantiomeric excess. So let's look at this. Percent enantiomeric excess. So we're talking about, mixtures, different amounts of enantiomeric forms of chiral materials here. This is the percent one enantiomer minus the percent of the other. Okay, so pretty simple there. So if we're have a percent enantiomeric excess of 0, that's what? Racemic, right? And so it would be 50 minus 50. Okay, they're rotating in equal opposite directions. Okay, if we had an EE of 50%, what would that look like? Well, the major one would be 75%, what, minus 25% of the other. These always add up to 100 there on the right, and this gives you an indication of what the excess is. You can picture it, 25% here is rotating in the opposite direction. That wipes out the effect of what? 25% of this one, which leaves behind 50% excess rotating in that direction of the major one. What's a little harder here is if you have ones that are not easy to calculate. 25% EE would be where the difference here is 25, which is 62.5 minus, 37.5. There are ways to calculate that and figure it out. Quiz or a test, I'd give you relatively simple ones like this, okay, to figure this out. So based on the optic rotation. So what it's always good to see here is think about 0, and then the maximum here, which would be the plus rotation, the minus rotation here. And if you're 50-50 between the two, yeah, you'd be in an optic rotation of 0. Here's the 100% where you're, 0 and all, the one that's rotating to the left. And then if you're over here, it'd be the other way around, 100% and 0 there, all rotating to the right. And then in between, here's your 75, 25, and here's your 25, 75 the other way, okay? But right in the middle at 0 is where they're 50-50. So you kind of have to recalibrate yourself. This qualitatively, I think, helps you keep track of it a little better. Now, that's another way to keep track of percent enantiomeric excess. Let's look at that. That's where you have percent enantiomeric excess can be alpha of the mixed over the specific rotation of the pure enantiomer times 100. Okay? So let me give you this. So let's say the specific rotation of pure form is minus 32 degrees, and you have a sample here that's minus 16 degrees, okay? So you're not sure what the ratio is of the enantiomers, but you know the pure one is minus 32, and your mix is 16. So yeah, it's pretty simple, right? This would be 16 over 32 times 100. So what is this? Oh, it's 50% EE. Okay. Oh, that's right. What we were talking about here, right? So that would be, you know, right there, 50% EE with the actual numbers, 32 and 16. Okay. So it's pretty good. Let me give you one that's a little harder here. We, in our lab a while ago, we had this reaction. We'd make this chiral molecule. Okay. It's an ester, an allylic benzoate ester. And the pure form we knew to be minus 119 degrees. And we did a reaction here with a catalyst, specific conditions. We took the optical rotation of our product, and it turned out it was minus 101. So what is the EE of this reaction? Okay, well, it's 101 divided by, what, 119 times 100, and that came out to 85% EE, which is pretty good, actually. Okay, and you can see, you know, 101 is 85% of the max, which is 119, okay? And it's a mixture of enantiomers. It's about 92 to 8%, okay? Which turns out to be about 85%. But those are some simple calculations. Either you know the percent of both of them, or you know the optical rotation of a sample, and you know the pure form, okay? So there's a couple ways to do it. All right, let's go back to one of the original structures we looked at before. And that's this here, this carboxylic acid and two stereocenters. And, you know, we're kind of going to make the relationship. There's two stereocenters, so there's four possible isomers. So if we look at the enantiomer of this first, we're going to invert all of them. And here I can give you the rotation, plus 9.5. Well, let's look at diastereomers here. Now from this, you can already tell quite a bit. You should be able to assign R and S to everything. You should be able to verify that those are enantiomeric. And you should be able to tell what the optical rotation of that enantiomer, right? So which one is this? This is the SS. So what's this here? We inverted both of them. That's the RR. And what's the rotation here? There it was plus 9.5. So what's this one? Minus 9.5, right? So you can already tell quite a bit here. Let's do a diastereomer here. Let's do the RS. So we just inverted that one, right? Now it's the R there. Let's see. And let's draw the enantiomer of that one. So that would be, what were they? Both up. And indeed, those are enantiomers over here. Everything else relationship-wise is what? Diastereomers. Do we know the optical rotation of this? Can we figure that part out? We can figure out the optical rotation of the opposite enantiomer. Well, what about the diastereomer? Yes or no? What do you say? Yes, can we figure it out? Or no, we cannot. I have to measure it. Yeah. So quite a few no's. Let's see what it is. Oh, it's minus 17.8. This is the minus, the lever rotatory, or the L form. Okay. Notice it's minus 17.8. This one was plus 9.5. There's no connection there. The connection here is to the enantiomer of that, right? How about this one? Once we know this one, the RS, now we have what? The SR. Now do we know the optical rotation of this one? How many say we can figure this one out now? Raise your hand. Okay, quite a few. How many say no? Okay. We'll do. So what is it here? Those of you who said yes, somebody know what the rotation is going to be? Plus 17.8. Yeah, it's the D form, okay, or the dextrorotatory form, okay. So you know that, again, no connection there, okay, except down here across the bottom, right, in the antimeres of each other. All right, let's do the polarimeter here, and hopefully this will show up. Yeah, you got to move this over here, and we're now in an analytical chemistry class, and I've got the polarizing filters here. And let's see, are they in phase? No, they're canceling out. Oh, there's the light coming through. Some of it anyway. Okay, maybe turn the lights off here. Let's see, where's that off? Okay, there we go. All right. Now these are two polarizing filters. They have narrow, microscopic slits there. I'm going to rotate it 90 degrees and look, the light cancels out. So that's why sunglasses are good. They take out all the incoherent light, just leaving one phase coming through, so the glare isn't as bad in your sunglasses, whatever. If I rotate back 90 degrees, we get the maximum amount of light. Okay, now let's put a sample in there. Here's a molecule, water. Is water chiral? No. Will it rotate plane polarized light? Nope. Okay, so let's see. So here's the sample now, and there's the light coming through the sample. You can see it jiggling, and the plane polarized light will rotate. And look, they both cancel out at the same time. So the light coming through the sample here was not rotated relative to the second filter. Okay, so you have to have the two polarizing filters in order to build a polarimeter, and this is what this is now. It's using plane polarized light to measure the optical rotation. Okay, let's find a chiral molecule. Oh, corn syrup, which is made out of glucose, the sweet stuff. If you don't believe me, you can come up and taste it later. That is corn syrup. Is glucose chiral? Yeah, it has a lot of stereocenters. It's very chiral. And this is thick syrup. Well, I don't know. Let's see how this works. Don't want to spill the water. There we go. Let's put our sample in. Let's reorient our filters there. There they are together, maximum amount of light. Let's put our sample in. You already notice a little color change. It kind of looks yellow. This is white light, so it's going to do some color changes for us as well. Let's rotate our filter. Let's cancel out the light on the outside. Oh, look at that. So there's light coming through the sample material. And why is that? Because now it's rotating that plane polarized light. Let's try to rotate our filters and get that light to cancel out. And this would be the rotation, actually. There it is, dark. You see there's light still coming through the filter. Now the polarimeter does this for you. It keeps track of how far it has to rotate the second observation to maximize the light coming through. It's all electronic, computer driven, but the basics of what I'm showing you here, we could calculate this plus 52 degrees with glucose on the overhead here. Let's keep rotating here. Notice a little orange. Back to kind of a yellow. So I'm rotating through the whole thing. The light blue is kind of pretty. And you can come up here and look through the polarimeter. You see the sample is changing colors too, which is kind of neat. And there we are. We kind of canceled out the light in the sample, but the light's still coming through. So we're just rotating, through infinity here to keep track of it. There it is again. The same view. You see, that's very different than the water, right? Where the light was canceled out in the sample as well as the side, where it's not going through anything. Anyway, okay, that's the basics of it. Yeah. All right, let's get back here to the overhead. A couple more things I wanted to show you on the overhead here. Yeah, we got a couple minutes. So what do we got? Oh, a bunch of chiral molecules, and morphine certainly got a lot of stereocenters there. Cocaine, we already talked about that. But that's not a stereocenter. That nitrogen position can invert the lone pair easily. That inversion is about 5 kcals per mole energy that can easily flip at room temperature. If it's in the solid state, that's a different thing. Then we do consider those nitrogens, if they're chiral stereocenters, as being an issue there. But you see a bunch of them there. And then here is a picture of morphine, just drawn a little bit differently. These are the pain-killing molecules, right? For chronic pain, morphine's still used in emergency situations in the ER, whatever, and on the battlefield, and a number of places where extreme pain comes out. Of course, morphine and the other opioid drugs develop tolerance and dependence. So these addiction effects are a problem. And there's been a lot of other analogs of morphine developed, including heroin. Heroin was one of the original analogs of morphine. It turned out to have worse issues with tolerance and dependence. But here's one here, salicylamine, or sal here. And there's just one stereocenter in sal, so it's a little easier to make. Here's the R form right here, and that's the stereocenter, okay? And the S form. And this is the magnitude of binding, or the effective dosage that inhibits 50% of the opioid receptor. It's through the opioid receptor kappa, I think, which is the important one for pain. And this is part of that receptor here, the protein, the blue part, and then the orange part is the drug binding in the active site of the opioid receptor. And so you see morphine's very potent at 20 nanomolar. That's 10 to the minus 9 molarity. That's very low concentration. Any concentration from there on up, the opioid receptor is bound and incapacitated. The pain signal does not come through the neurons, okay? So can we do it with a simpler drug like this, like sal? Well, it turns out the R form is in the millimolar range, 600 millimolar. That's not very potent. R sal here it is. Here's morphine bound to the same active site. And the two crystal structures are known for the R and the S form of sal. And this one kind of has the methyl group pointing right into this side chain amino acid, okay, which is aspartic acid, D147. Those are the numbered amino acids on the protein backbone, if you know anything about proteins. But this binds that same orientation, but it sticks right into aspartic acid there with that methyl. Whereas the S form is more potent. It's at 9, micromolar, 10 to the minus 6 molarity, which is still pretty potent, okay? But what you need to see here is the physical properties of the two enantiomers are different. Everything else is the same, melting point, boiling point, NMR spectra. But what do we say? Optical rotation, which would be opposite here for the two sals. Okay, same magnitude, but opposite rotation. But, and then what's the other property? Binding to a chiral molecule, which is this chiral receptor. This one has pretty good potency here at 9 micromolar. This one has pretty poor millimolar, many orders of magnitude less potent. They're both less potent than the actual natural drug morphine, but this points out that other property, right? That it's not just the optical rotation difference, it's also the difference with biological activity. So when drugs are studied now, the FDA requires that we study all isomeric forms of a drug to make sure it's okay because, naproxen, here's the potent form, the S. The R form is actually a liver toxin. Oseltamivir is this antiviral drug. It's a lot of stereocenters, you can see there. And then right here, okay, so we mentioned thalidomide before, right? It was held up by the FDA in the early 60s. It causes birth defects. And it was this person right here, Francis Kelsey, who won a Congressional Medal citation here from this guy. You know that guy, right? John F. Kennedy, president. He was actually shot just a few weeks after this picture was taken. But he recognized Francis here for keeping this drug out of the U.S., and we didn't have the same problem with the developmental issues like they did in Europe. Anyway. So that's a great example, I think, there. Chiral molecules, just to remind you there. Sorry, we went a little over. That's it for Chapter 5. Chapter 6 coming up next time. Very good. We'll see you then. Okay.